Now, let me come back. In the second half of 1971, I don't exactly have the sequence right here, but Vern Schatz again entered the scene and complained again that the 10-digit code was probably going to be obsoleted. So we had another brainstorming session. We said, aha, we could have another number, let's call it the number system designator, that preceded the 10-digit number that actually identified different code systems. Each code system didn't have to be 10 digits. It could be 11 digits or 50 digits or however many digits we wanted to designate. It could be used to subsume other codes. I'll come back to that point. And so we added the number system designator to the 10-digit code. And I remember now one of them, and I forget the number system number, but I think it was 9 or 10 or whatever, doesn't matter. That code was designated as a code of 13 to 35 digits. Now at 35 digits, you can write that number, write 35 zeros, and you'll get a number that will be sufficient to cover all the grains of sand in the world. A big number, a really, really big number. And so we were able to accommodate Vern's concern, but we also managed to accommodate some other issues like coupon identification, like the National Drug Code, which I'll come back to. But I can tell you this, that Vern's courteous but forceful criticism was well received and in fact resulted in that change. Somewhere along the line, I don't think it was then, but shortly thereafter, we added yet another digit at the end of the 10 digits, and that was called the modulo check digit. And that is a simplistic, not simplistic, fairly sophisticated process where you add, subtract, multiply, divide, and whatever, all the code numbers that preceded it, and that created a number so that if you read that number, it effectively told you whether you had misread any of the other preceding digits. A very powerful concept, and I don't recall who recommended that, but we did incorporate that. George Lauer. George Lauer, that's the guy. From IBM, added that little concept. Turned out to be a big concept because it basically, that plus another thing I'll come to, produced a symbology that was virtually without error. Now we reserved 0 in the number system designator for the grocery industry, and at this point Marvin Mann entered the scene. Remember I told you that that we really didn't get a lot of support or involvement by IBM until Marvin got there. When Marvin got there, the floodgates opened. We had people calling from all over the world from IBM offering ideas and insight and suggestions, and ultimately, although it was a bit of a push, they ended up agreeing to do a test at the Battelle Memorial Institute. I'll come back to that, but all I can say is we were blessed by IBM's willingness, because they now believe that we were for real and they were in the game, and they were really in the game. A couple of things came from those early interactions with IBM, not just the modulo check digit, but we also learned the power and importance of the encodation and the accuracy required that was linked to the encodation. We also learned about how important the ability of the printing and packaging industry was in terms of holding the required dimensional tolerances, which obviously was a very important factor if you were measuring the width of a bar or the width of several bars or the distance between bars. And they made another powerful point, and that is, don't worry about the technology of the scanner computer to deal with the complexity of a symbol. The complexity of a symbol can be handled through automation, and so don't sacrifice the solution for fear that the computers that are evolving will be unable to deal with that complexity. Not a problem. So think in the future, and I'll come back to that point. Well, let me do it now. We, at some point in here, solicited help from Mary Eden, who was then an automation expert at MIT, Alan Haberman, who lived in the Boston area, was able to get Murray to come in, and he then took all of our work, our analyses, our thoughts, our concepts, and basically concluded that the process we were conducting and the alternatives that appeared viable were consistent with technologies that would be good for decades and not obsoleted in the near future. So last point under IBM, he made the point and provided data that came from various IBM laboratories that key entry was simply not sufficient to gain anywhere near the productivity enhancements that we all sought. Okay, at this point, the code committee is moving into high gear. Remember the problem with the Campbell's tomato soup packed out as 12s and 24s, and so the case code, item code problem got resolved. But there's other problems. What is an item? What is a, let's take a 6-pack of beer. Is the item the 6-pack or is the item the beer can? Because sometimes it's sold as a beer can, sometimes it's sold as a 6-pack. They had to resolve that. And I'll leave you to read all of the various documents and instruction manuals so you'll know how they resolved that problem, which was pretty difficult. They also then formed what became the UGPCC, which was a step beyond just being a committee, and that led in time to a very highly structured, very large, and not very large, but a large organization that deals with the entire administration of the code and the symbology. Now, at this point, we had to get real serious about how to print whatever symbol was going to be selected. And so we began discussions with various packaging trade organizations, with printing institutes, many of which were all running their own various tests and evaluations. And so we began to grasp the vast array of substrates, printing technology, and ultimately coatings. Now, just for fun, I'll tell you that quite a bit later from this, I ended up doing a leveraged buyout. I bought 2 printing companies that were in the sheet-fed printing business, and had a ball. Ultimately, sold them, and anyway, that's all history. The Symbol Committee began interactive discussions with equipment manufacturers. This is an extraordinarily important step, because we would go to, let's say, Pitney Bowes, who had a symbology, happened to be a barcode, and they offered up questions that we could ask IBM. And we'd have a meeting with IBM, and we'll say, well, we got a couple of these questions here, and it has to do with bit rate and error detection and so forth. And at first there was silence. Then they figured it out pretty quick, and they said, well, yeah, they answered the questions, and then they gave us questions for Pitney, and questions for Zellweger, and questions for RCA, and then we'd go to RCA, and they would have questions for Zellweger, and so forth. And so we got an education in some of the most sophisticated approaches for scanning technology and invention that the best in the world could come up with. We also began to really understand the linkage between the limitations of printing accuracy in the packaging business and the scannability and accuracy of a check stand scanner. Now, out of those meetings with the equipment companies, we came to about 5 or 6 very important, let's call them tentative conclusions. The first one was that achieving omnidirectional scanning was absolutely crucial for the productivity enhancements. However, it did not mean that we needed a bullseye, which was inherently omnidirectional, because the laser didn't have to go just back and forth. The laser beam could in fact traverse a complicated pattern, thereby allowing the computer to assemble the numbers correctly and read the symbol. So omnidirectional, yes. Bullseye, not necessarily. Number 2, the symbol printing tolerances were pretty important, and there were high levels of expectation among the various companies developing scanning technology. I mean, technology, these guys, amazingly, some of them were not well versed in the capability of the printing and labeling industry, even people who made bottles with labels. And so we had to understand, and then we had to deal with the various limitations that were in the real world. The next thing we came away with is the fundamental importance of the encodation technology. Now, when I say encodation, what I mean is translating the bars to numbers. And in the final symbology that we'll discuss in a minute, there are, in fact, 2 bars for each character, and the width of those 2 bars was limited to 7 sections. Let's call them bits. If you're in the computer business, they were really, that's what they are, bits, 7 bits. Now, if you have 7 bits and you could use any number of bars, how many possible numbers could you have? Well, the answer is 7 squared, 49. Now, let's suppose that you said, no, I want to only have 2 bars. Okay, we'll have 2 bars and we only have 7 bits. How many possible combinations are there when you make that limitation? The answer to that is 24. Oh, well, 24 is higher than 10, so that looks like a good idea. I'll come back to another point later on with regard to the ultimate symbol selection. But we now have, in effect, 24 combinations of bits with 2 bars to make up the characters in the symbology. The next thing that we learned was the importance of bit rate. That is the speed at which the computer and the scanner can absorb information and translate that into a number and then look up the price so that you got the productivity that you needed. And we got to be pretty expert in asking questions about the bit rate of the various equipment that was suggested. And then another thing that came out of those discussions was the issue of multiple symbols at a time. For example, if you put a symbol on an individual beer can and you put a 6-pack across, what answer would you like to get? 1 or 6 or a 6-pack? And so these things were fundamentally important, but fundamentally it came out of our education process with the various equipment manufacturers that were all striving to convince us that they had the ultimate solution.